So this week we are going to continue with the organic synthesis topic. We're going to build on what we learned last week, where we looked at the very basics of organic synthesis. We thought about nucleophiles and electrophiles and how they are involved in reactions with haloalkanes, which are really useful starting materials for organic synthesis because they contain that polar bond, which is prone to nucleophilic attack. This week and for the next couple of weeks, we're going to look at different families of organic compounds, and we're going to concentrate on alcohols and ethers this week, which are two fairly closely related groups of organic compounds. We're going to think about their properties, why they behave the way they behave, and why they're so useful. We're going to think about the preparation of them, so how we make them. And we're going to think about the different reactions that they can be involved in. We're going to start by looking at alcohols, so maybe worth pausing the video here and looking back at your higher notes and just re-familiarise yourself with naming alcohols and classifying alcohols. So just a very quick recap about what an alcohol is. They're essentially substituted alkanes, where we have replaced one of the hydrogen atoms with our hydroxyl group, which is OH. The hydroxyl group in an alcohol is known as the functional group, and that is the part of the molecule that makes that compound the class of compound that it is. So because it has a hydroxyl group, it is an alcohol. The names of alcohols always end in "ol". We can classify them as primary, secondary, or tertiary, depending on the position of our hydroxyl group. So if we look at the example we've got here, we've got two carbon atoms, so it is ethanol. And because the carbon atom that our hydroxyl group is attached to has two hydrogen atoms directly attached to it, this is a primary alcohol. You may see different sorts of alcohols. You may see an alcohol that has, rather than one hydroxyl group, it might have two hydroxyl groups, and that would be known as a diol. You might see alcohols that have three hydroxyl groups, that would be a triol, and the most common example of a triol that you will have come across before is glycerol. So we're going to have a think now about the properties of alcohols. We're going to think, first of all, about boiling point. So let's think about our hydroxyl group. So it's this hydroxyl group that makes an alcohol an alcohol. And what you should remember from higher is that when you have a hydrogen atom directly bonded to an oxygen atom, we will see hydrogen bonding. Now, hydrogen bonding arises when you have a hydrogen atom that is bonded to a much more electron-negative atom, like oxygen, which also contains lone pairs of electrons. So all of these oxygen atoms here contain two lone pairs of electrons each. We'll see this arise also if the hydrogen is bonded to a nitrogen atom and a fluorine atom. Now, because the oxygen is more electron negative and it contains these lone pairs, the bonding pair of electrons will be pulled much more significantly towards the oxygen, setting up this polarity here. So you've got our lone pairs of electrons and our bonding pair closer towards the oxygen. So that polarity is quite significant. So that means when it comes in kind of close to another hydroxyl group with the same significant polarity, we're going to set up these intermolecular forces, and these are the hydrogen bonds. Really important to remember that the hydrogen bonding is not your covalent bond, holding your hydrogen to your oxygen here. It is the intermolecular force that keeps those different molecules quite closely pulled together. Hydrogen bonding is a lot stronger because of the stronger polarity. They're a lot stronger than something like a London's dispersion force, which is pretty weak and only exists very momentarily. Extra energy is needed to overcome them, which is why alcohols have higher melting and boiling points than other compounds which might have a similar mass and shape. And in a few slides time we're going to compare the boiling points of alcohols and ethers, which should highlight this to you. So the second property of alcohols that we're going to look at are their solubility. And solubility is directly related to how big the alcohol molecule is. So hydrogen bonding is the force that is responsible for the miscibility of alcohols with water. Miscibility basically just means how well an alcohol mixes with water. So if you have one of the smaller alcohols, so there is ethanol, it only has 2 carbon atoms. By lower alcohols, we mean fewer carbon atoms. It's got this really polar end of the molecule here, which will form hydrogen bonds between the water molecules and the alcohol molecule, and that will allow them to mix quite well. It has a really short chain. There's only 2 carbon atoms in there, so the molecule overall is pretty polar, which means it will dissolve in water quite well. But if we think about a larger alcohol, so let's take this one here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms. So that's decanol. It has this much bigger carbon chain, okay? So that carbon chain consists of 10 carbon atoms, and it will consist of 21 hydrogen atoms. That carbon chain is hydrophobic. It's non-polar. It will not form hydrogen bonds with the water molecules, meaning that it won't pull them into solution basically. So if it's got this polar end here, it's negated by this much larger hydrophobic chain, meaning that they will not dissolve in water. So basically, smaller alcohols will dissolve in water because the polarity is great enough to form these hydrogen bonds. But with your larger alcohols, the hydrophobic chain makes that not possible. So we're going to have a wee think now about the preparation of alcohols, and there's 3 different ways you need to be aware of. The first way is nucleophilic substitution of a haloalkane. We would carry this out using a strong base which provides the hydroxide ion, which would act as the nucleophile to carry out that reaction. The second way is by an acid catalyzed hydration. So we would take an alkene. Our alkene would relate to whatever alcohol it is we want to form. So if we want butan-1-ol, we would use but-1-ene, for example. And then the third way is taking aldehyde or a ketone and reducing it using an agent such as lithium aluminium hydride or sodium borohydride, which are both really strong reducing agents. This is essentially just the opposite of the oxidation of alcohol stuff that you looked at in higher. So the first method of alcohol formation that we're going to look at in detail is the acid catalyzed hydration of an alkene. In this reaction, we have the hydride ion, the H+ ion, acting as essentially as a catalyst. It behaves like an electrophile because it is electron deficient. And if we look at our alkene molecule, we've got propene here, and The reason alkenes are quite reactive is because the double bond is electron rich. Remember, between the sigma bond and the pi bond, there are 4 electrons taking part in the bonding there. So because that is electron rich, it can behave like a nucleophile. So in the presence of this really electron deficient species, the reaction happens. The double bond breaks and jumps on to the hydride ion. We form this intermediate here. If you have a look, we've got our carbon, which has a positive charge, making this a carbocation intermediate. Carbocation intermediates are extremely reactive and will pretty much react straight away. So you introduce water into this reaction here, and remember the oxygen here has 2 lone pairs. It can be pretty reactive and can behave like a nucleophile, so will attack the positive carbon in our carbocation there pretty quickly. And that will form this protonated alcohol. Protonated because it contains an extra hydrogen atom. That is not a species that is very stable. It doesn't like to exist for very long. So what happens is this bond breaks and we get our hydrogen ion back, and we have our propantuol alcohol here. So the next way that we can form an alcohol is through the reduction of an aldehyde or a ketone. Maybe a good point to have a wee quick glance back at your higher notes. Refamiliarise yourself with aldehydes and ketones, remembering the difference between them is that in an aldehyde, your carbonyl group is on an end carbon, and in a ketone, it's in one of the inside carbons. When you learned about aldehydes and ketones, you also had a wee think about the oxidation of alcohols. So aldehydes are formed from the oxidation of primary alcohols, and we would use something like a hot copper 2 oxide catalyst or acidified potassium dichromate. The reduction of aldehydes we do using a reducing agent rather than an oxidizing agent, and it's just the reverse reaction of everything you learned at higher. Really common reducing agents are lithium aluminium hydride and sodium borohydride. So a wee bit now about the different reactions of alcohols. Alcohols are some of the most useful organic compounds. They are the starting materials for a whole host of extremely useful reactions. We're going to go through a few just now. We're going to have a look at the dehydration to form alkenes, which are themselves really useful starting materials. We're going to look at the oxidation. Well, actually, we're not going to look at that because this is all covered. If I just put my pen on, this is all covered in higher. So if you have a wee look over the oxidation of alcohols from higher, we're going to look at how we form ethers, which we have touched on already, but we're going to look at how an alcohol can form an ether, and the formation of esters, which is also something you've looked at higher. So maybe take a wee minute to refamiliarise yourself with those 2 uses of alcohols, and we'll have a look over the other 2 right now. So one of the most common ways of forming an alkene is by dehydrating an alcohol. It's a dehydration reaction because we are eliminating a water molecule from our alcohol. This can be done in one of 2 ways. For our smaller, more volatile alcohols, we can vaporise it and pass that over a hot aluminium oxide catalyst. And we can also do the same thing by treating the alcohol with either concentrated sulfuric or phosphoric acid. Now here we have an example here, we have butantuol. That's what we're starting with. Now, depending on whether we remove this hydrogen or this hydrogen, we might form our double bond here, or we might form our double bond there. So there are two possible products from the dehydration of butan-2-ol. We can form either but-1-ene if we remove this hydrogen, or we can form but-2-ene if we remove this hydrogen. So another useful reaction of alcohols is the oxidation of alcohols, which you, as I've said before, should be aware of from higher, but just a very quick bit of revision. If you have a primary alcohol, you can oxidise that into an aldehyde, and that can be further oxidised into a carboxylic acid. If you have a secondary alcohol, that is oxidised to form a ketone, but it cannot be oxidised any further. And a tertiary alcohol, you cannot oxidise before it at all. So remember, reagents used are things like copper 2 oxide or acidified potassium dichromate, or Tollens reagent, Fehling solution, which remember is also known as Benedict solution. So a further reaction of alcohols is in the formation of ethers, and we can form an ether from an alcohol in two steps. We first of all have to form an alcoholic alkoxide, which was mentioned last week very briefly. And we do that simply by adding an alkali metal, either sodium or potassium, to an alcohol. Now, the alcohol that we use will determine what alkoxide we form. So if we want to form a methoxide, we would use methanol. If we wanted an ethoxide, we would react our alkali metal with ethanol. This, we form essentially an ionic compound here, and this is our alkoxy group. That alkoxy group then behaves like a nucleophile, it is a nucleophile, and attacks the carbon in our polar carbon to halogen bond, which then kicks on to the chlorine. Remembering all the time, because I'm harping on about this, the reason it attacks that carbon is because that is a polar bond and that is susceptible to nucleophilic attack. Then the final reaction of alcohols that we're going to look at is in the formation of esters. You first came across this at higher, and so this should just be revision. So remembering that in order to form an ester, we take an alcohol and we take a carboxylic acid, and they undergo a condensation reaction. You probably had a go at doing this in the classroom at higher if we weren't at home by that point. But so if you have propanol and ethanoic acid reacting, we would take the hydrogen from our hydroxyl group in the alcohol and our hydroxyl group from the carboxylic acid. It would eliminate a water molecule. It's a condensation reaction, and then we would form our ester group here. So from these two substances, we would form propylethanoate. Remembering that this has to happen with a catalyst, and that catalyst is usually a concentrated sulfuric acid catalyst. It's really important to remember that it's a concentrated acid catalyst that we use. So the second way of forming an ester from an alcohol is using this new compound to you. This is an acid chloride, and instead of an OH group, which would give you a carboxylic acid, we have a chlorine. So your OH is replaced by Cl. This is called an acid chloride, and it reacts in exactly the same way as the alcohol would react with a carboxylic acid, but the reason this is actually a more commonly used method is that it is much faster and it does not require a catalyst, whereas the other one does. So this point at the bottom here is really important. So a really common question, why would we use an acid chloride? It's because it is much faster and does not require a catalyst. Other than that, the exact same thing is happening. It is still a condensation reaction. Just because water is not being eliminated, it's the hydrogen chloride molecule here. So a small molecule is still being eliminated, so it is still classed as a condensation reaction. Right, so the final class of compounds we're going to look at this week are ethers. Ethers are most commonly used as organic solvents. We use them because they're polar, but not too polar. They're good at dissolving most organic substances, and they are not very reactive. So we're going to have a quick look this week at how to name ethers, some of their properties, how we prepare them, and their uses. So the easiest way to think about an ether is just the same way we would think about an alcohol or any substituted alkane. One of the hydrogen atoms has been replaced with a functional group. And in the case of an ether, that is an alkoxy functional group. And the type of ether that it is determined by, first of all, what the alkane is, and secondly, what alcohol you use to prepare the alkoxide, which we've looked at before. So this is the functional group with R and R1 here just representing different lengths of alkane chains. We can classify them as symmetrical. Symmetrical ethers are when R1 and R2, so your two different alkane chains contain the same, they're identical. And we can also classify them as asymmetrical, which is where your two alkane chains are different. Right, so we're going to have a wee think about naming ethers. Have a wee read through this point. You can pause it or whatever, have a wee read through the slide. It will make much more sense when we're actually looking at examples, but what I want you to get from this is we have to look at our ether and look at both parts of it. If it's symmetrical, it's quite easy to name. If it's asymmetrical, we have to identify where the larger alkyl group is and where the smaller alkyl group is. The larger alkyl group will give us the end of the name, and it is just like naming a normal alkane. And the smaller group we call the alkoxy substituent, and that comes at the beginning of the name. So let's have a look at some examples. Here we have our functional group. So let's have a look. On this side, we have 3 carbon atoms, and on this side, we have 1. So this whole section here, we would classify as our alkoxy substituent group. So because there's 1 carbon atom, the name would start methoxy. This gives us the ending of the name. There are 3 carbon atoms, which is prop. So this would be called methoxypropane. So here we have an ether with a skeletal structure. We have 1, 2, 3, 4 carbon atoms on this side, and 1, 2, 3, 4 carbon atoms on this side. So nice and simple, it doesn't matter. Butoxy, butane. Now a wee bit trickier here. If you notice in these 2 examples, our ether is almost in a complete straight line, in that our alkoxy substituent is attached directly to one of the outside carbon atoms. Here we have an example where that's not the case. We have our alkoxy substituent, which is this whole bit down here, so this blue bit including the oxygen atom, is attached to the middle carbon atom of an alkane chain. So we have 1, 2, 3 carbon atoms there. So we've got 3, we'll just start the same way, versus 2. So this is our chain. So we would call it ethoxy. We need to number what carbon atom in the longer chain that it is attached to, and it's attached to carbon number 2. So we would call this 2-ethoxypropane. So I mentioned earlier about the properties of alcohols and how we were going to compare them to the properties of ethers. And I want to just take a minute to do that now. So I have 2 isomers here. We have ethoxyethane and butan-1-ol. They both have the formula C4H10O. But if we have a look, the boiling point of butanol, butan-1-ol, is much higher than the boiling point of its isomer, the ether. Now I'm sure you could have a look at this and work out why. Let's compare the bonding. Butan-1-ol contains an oxygen directly bonded to a hydrogen. That sets up an extremely polar bond because we've got lone pairs and a higher electron negativity on this oxygen. That allows for the formation of hydrogen bonds with something else that contains that group. Okay, just put R there. The ether doesn't have that. The ether doesn't have that extremely polar situation that the alcohol does, so it cannot form hydrogen bonds. We know that hydrogen bonds are the strongest of the intermolecular forces, so require much greater energy to overcome, to break them, which is why alcohols have much higher boiling points than ethers. But have a look at the solubility. The solubility is roughly the same. Right, so just to go over once more about the preparation of ethers, it's obviously something we have touched on before. So it just involves standard nucleophilic substitution of a monohaloalkane, as we've looked at before. We do that using a metal alkoxide, which we prepare by adding a alkali metal to an alcohol of our choice. So if we want our alkoxy substituent group to be an ethyl group, like an ethoxy group, we would add our alkali metal to ethanol, for example. So it's quite easy, and then to determine other ends of the ether by what monohaloalkane we use. So it is quite easy to do. So just once more about the reaction mechanism here. We've got our polar bond, which is attacked by our nucleophile. Now, having a wee think about whether this is SN1 or SN2, have a look at our monohaloalkane. It's methane. The carbon that our halogen is attached to has 3 hydrogens attached to it. So it's a primary haloalkane. So there is enough space for it to react via a transition state rather than a carbocation. So it is SN2. So I'll just draw that out for you. Remember, we draw our transition state in square brackets. So I'm going to start by my alkoxy group and the bond half formed here. So C2H5, and that bond has half formed to my carbon. Up here, I'm going to put this hydrogen and then these 2 hydrogens, which I'll just draw in using the same 3D bonds. And then at the same time as that's happening, the bond to the chlorine is breaking, and that has a negative charge. And as that reaction fully happens, this is the product that I get. So very final slide for this week is just a little bit on the uses of ethers, which you can sit and read through this yourself. But an important thing to remember about ethers is because they have a degree of polarity, they are widely used as solvents. They can dissolve a wide range of different organic compounds, but at the same time, they are relatively unreactive because they don't contain that really polar hydroxyl group. They're resistant to oxidation and reduction. They tend to be quite smaller molecules, so are quite volatile. So once we've carried out a reaction in an ether, it's quite easy to get rid of it through some sort of distillation. So that's that for this week. Just the usual, I've put up some questions on alcohols and ethers. Work through them, send me your work, get in contact if there's anything you need a hand with.